Good? Okay.
All right.
All right, so today we're going to talk about OpenShell working with GitHub. We'll start off with giving you a quick overview of what OpenShell is, and then we'll leave some time at the end for a demo, and then we'll jump in. So a high-level view, OpenShell is a project that Alex and I started at NVIDIA on our sort of 20% time about 8 months ago. The core thesis around OpenShell was really around two sort of first principles. One was around the fact of, as we're moving towards an agent world, what does an agent-native software stack look like? And our core thesis was as you want agents to be long-running, they're switching to stateful, long-running sessions, managing persistence, you really need a different environment than a whole new stack for them to be managed. And we'll sort of talk about what that looks like. The other pillar of this is that if you have an agent-native software stack, then the tooling for it should really be built for machine speed. So how do you build machine speed as well as an agent-native stack? And the way we came about this is that ultimately what we really need to be able to instill is a trusted runtime. So the core thesis we came around is how do you make this secure by design, and how do you make it a trusted runtime so everyone can have the trust and the confidence to run agents, models, harnesses inside this environment.
Just to add a little bit to that there, I think we've all used coding agents. You all get frustrated when you have to keep approving different things inside of a sandbox or for access. We start out with the question of what happens when we're running 500 or 1,000 agents at the same time. What would that look like? So trying to figure out how we can apply technology in a enterprise-grade way to approve as many agent actions as possible in a secure way to, as Ali was calling it, build at agent speed, but don't be dependent on human inputs to keep going.
So one of the core things about OpenShell is that the environment itself is a zero trust. So it's not completely permissive. Every sandbox, every environment starts completely closed down. And then as the agent is basically granted access and additional components, it can move. Now, the way we sort of thought about this is, and I'm not going to read everything, is this. These are some of the big categories we hear from our partners, from our customers, from the ecosystem as to the things that really concerns them about running long-running autonomous agents. And the way, if you sort of go through this, one of the things you realize is a lot of these types of controls and governances are enforced at the agent layer, at the model layer, within that probabilistic loop. So the way we thought about runtime and OpenShell was how do you take these policies and how do you create a deterministic way to control and govern the agent? So you have to bring that policy, that governance to the infrastructure layer, to the kernel layer. And a good example is, for example, prompt injection. The design that we have is the agent should not really have any credentials, secrets, tokens, keys if it's authenticating against a service. So the gateway outside the sandbox holds all that. The sandbox is the blast radius. So if there's a prompt injection, if something happens to the agent itself, nothing for it to leak, and the blast radius is a single sandbox. And for those of you who are sort of familiar with traditional cloud-native primitives, it's like when we went from stateful monolithic VMs to container-based microservices on Kubernetes, you can now start to treat these things a little bit more like cattle than pet, and as a result, it becomes a little bit easier to govern. So this is a high-level overview of an architecture of OpenShell. Now, a couple quick things I'll mention right away is OpenShell is entirely open source. It's under Apache 2.0. Everything you're seeing here is on our GitHub repo, including the roadmap, the architecture, and everything around it. I'll give you a quick high level of the primitives that come with OpenShell. So as we mentioned, OpenShell is a runtime. In this runtime, there's a few critical primitives that come with it. One is really the gateway that sits outside every sandbox. The gateway is meant to communicate and interact and hold credentials and tokens and keys as we talked about. So every agent has this session, but it has no way to be able to leak anything else. Every agent or its sub-agents or its tooling runs its own dedicated sandbox. So if you have an agent that spawns sub-agents, those can run into their own sandbox and have cross-sandbox communications. Now, as part of this, one of the things we thought very hard about is how do you enforce policies that ensure not just what policies enforce, but the policy can answer the question of, if I enforce this policy, what can this agent still do? And that's where we actually created a very unique offering called the Policy Prover. Maybe I'll have Alex talk a little bit about the Policy Prover and sort of the unique things, because we're going to demonstrate this in a demo at the end as well.
Yeah. One quick thing about the architecture as we dive in, I think a lot of us are very familiar with agents running inside sandboxes and that kind of environment. I'd say an architectural departure here, it's a little bit different, is normally when we're using Copilot or we're using Claude Code or anything like that, you have the agent, and it is executing code inside of a sandbox. The agent itself isn't running inside of the sandbox. And then the governance you get is done at the layer of Copilot, or some of the layer of 𝗦𝗲𝗀, or whatever you're using. In the OpenShell world, that agent runs inside of a sandbox. It's able to spin up new sandboxes, but every input and output that it has is enforced. And so that's a really neat thing. It doesn't matter. You can have like one policy language that works across any type of agent that you're running across your infrastructure. Over here, we see this thing called a policy prover, and this is one of the unique areas that we've developed with OpenShell. Actually uses some technology that came from Microsoft originally. So what we did is we took the policy language. I'm going to get into the weeds here a little bit. We use OPA and Rego or YAML, if you guys are familiar with these like standard policy languages. And we described it in formal logic. So if you guys are familiar with formal verification, SMT solvers, things like that, what this allows us to do is not just like have an if statement that says, can this agent still access the internet? Can it like write to a repository? We can actually create a mathematical proof of that. And you can do incredibly complex and neat things with this. So this is a unique area that we added in. If you look at where I would say kind of the puck is going, and this is what we're going to show in a demo for you guys in a little bit, you see, okay, we need to get out of the mode where humans are sitting there waiting for every single thing to happen and then approving every entry. You would see, I'd say like OpenAI and Anthropic are both really starting to talk about using another trusted agent to review this sandbox change and see if it's okay. So it's like auto approver for Codex, managed agents for Claude. They're still susceptible to the same risks though, right? You have another agent that it's just like a human, could also be fooled. The policy prover is a really neat input or complementary thing that you can have there where the policy prover cannot be fooled. Assuming that our description of the logic of the policy is correct, if you are opening up a new hole in the sandbox to allow it to write to a new repo in GitHub, for example, there's no way to fool an agent into not seeing that you're doing it. The prover will see it and it will highlight that. So pretty interesting technology thing. Another thing I think that we'll show in the demo is how fast this runs, right? So as we add like more and more layers of security, the risk is if you're having, for every call that you have with your agent, if another agent has to review it, you're doubling your token costs and you're doubling your time. The prover can run in order of single-digit milliseconds, so often it's not even required to do that at that second level run, so there's some neat kind of performance benefits in there as well.
And then the last thing I'll add on this particular slide before we move forward is our privacy router. So everything we've built in OpenShell runtime is thinking around how do you create isolation around system, file, network, memory, sort of all the constructs that you typically want to be able to slice your environment. But the other thing we think about is OpenShell is really isolation around agentic behavior. So if you think about something like traditional encapsulation, right, like whether you're talking about gvisor or hardened containers or micro VMs, in a lot of these cases, you're just adding additional layers between a process and a kernel. You're trying to really reduce attack surface. Agentic behavior is very different. It sort of manifests itself in very different forms and environments. So the privacy router borrows actually a lot of the work that we did around synthetic data. So Alex and I joined NVIDIA about a year ago. We founded a company named 𝗦𝗲𝗀𝗀. We focused on synthetic data. So the privacy router uses a lot of technology that comes out of synthetic data, actually a lot of work that Microsoft itself did. And I'll describe it in sort of 3 use cases, which is better than just kind of getting under the hood. So one is you might have an environment where an agent needs to, for example, run inference. And the data it has is riddled with PII. So once that agent submits that query, the privacy router looks at it, says there's PII in here, routes it to a local model for inference. There might be a second scenario where an agent requires to run inference. It requires multi-turn, orchestration, tasking, reasoning, and it needs to go to a frontier model. And it sees there's actually no PII in this, so it lets it route out. The third one is really the combination of the first two. And this is where we can use a combination of things like Kleiner models or differentially private fine-tuned models, so use DP with low epsilons to synthetically rewrite the query so it maintains the utility but none of the PII. So you can still go out to a frontier model, reason, and come back in your environment and rehydrate it. So it's a way to basically keep context and PII local while leveraging global compute. So jumping maybe into the demo and sort of talking about what we're just going to show you very quickly in the demo. Alex, do you want to just quickly talk to this?
Sure. Yeah, we have 2 demos that we're going to show today. The first one is in the time that you're running multiple agents, addressing the issue of persistence, right? So like you have agents running. It's awesome, this idea of like ephemeral agents. They spin up, they do their job, they spin down. How do you enable those agents to communicate to each other? How do you enable them to store data? And so one of the things that we're going to show here is actually using GitHub as a persistence layer. It's actually really neat. Whereas the agents run, either the artifacts they generate at the end or their notes or the whole audit trail, you can actually just store that to GitHub. So that'll be the first demo. The second demo we're going to show right after that is talking about this whole kind of like loop where the agent actually, we'll talk about this, but like within OpenShell, the agent has the ability to negotiate its own access with the supervisor. So we'll demonstrate how that runs and how we can reduce some of the kind of human overhead for like approving different things as these agents evolve.
And I think one of the key things around OpenShell and how we think about policies is when you write global policies and say these particular actions are allowed or disallowed, all of those global policies are made available to the agent running inside the sandbox. So this is an area where, because we start with a zero trust mode, the agent doesn't actually have access to everything. But because it has understanding now of all the policies allowed in your organization, it can come back and say, if you give me X, Y, and Z, I can go complete my task. But that is also not given blindly, because what we've seen is agents can actually combine different chains and be able to problem solve. So once they request that, the policy prover runs on top of it, ensures that there's no accidental exfiltration path created, and from there the policy is then granted to the agent. And then sort of if you extrapolate this, this is really why this is important, because when we talk to partners who are doing this with millions and millions of sandboxes, then that becomes very critical, because even 1% approval to human looks like thousands of prompts per day. So this is really how we're trying to automate this process.
I'm going to start a demo here. This is one of the core examples we have on OpenShell. So if you just go to OpenShell, go to examples, it's right there. What we're doing right now is demonstrating one of the ways we can use GitHub for agent as a notepad. Is the simple kind of example we're using here. So what's neat about this? You can restart your sandbox as many times as you want to. Concurrency is built in. You're never going to have to worry about stomping on other agents' notes or anything in GitHub. It's very cool. So what we're going to do essentially is we're going to follow kind of a standard map reduce or fan out pattern, where we're going to use OpenShell. We'll demonstrate this in a second. We're going to fire up 5 sandboxes. Each one of them is going to work on a task. They're going to store their notes, and then we're going to have another summarization or like a synthesis agent go across all those notes and combine them into one single result. All that's going to be stored in GitHub. Kind of cool stuff that we're showing here. So this is what a policy looks like inside OpenShell. So this is the OPA Rego policy, but here you can see, for example, here's what a scoped GitHub policy would look like that's scoped to a single agent execution. So we're telling it, this is what you're allowed to do. You're allowed to access these very specific REST endpoints. If you need more, you need to negotiate it, but it's always kind of like that. It's really important security construct, this really minimal policy. The second thing that we're showing here too is that the agent itself will never actually see the credentials. All of that is managed at the supervisor level. So here I'm going to open up a terminal here. So this is the terminal interface for OpenShell. It's a developer-friendly interface. We can see what's happening. We're running a demo here on the left. What we just did is we spun up 5 sandboxes. Each one of them is working on a task. So it has a coding agent inside of it, a Copilot or Codex in this case. You can see here that it's hiding the credentials from the agent. We have 4 sandboxes that are running on the task right now. They're going to use the credentials we granted for them to write directly to GitHub when they're done. We'll show you what this looks like. And then the synthesis agent's going to take all of those different results and put them together. But the neat thing here is we're seeing the communication where each agent is isolated in its own sandbox. You can reason exactly about what it's doing from a security perspective. And then we've got the ability for them to coordinate together. I'd say like a slightly more advanced example, if you guys are looking to build on this, there's a neat protocol from Google called A2A, so the agent protocol, that enables the agents to, for really fast, high-rate communication between agents, if they're like working together on something, they can do that. This mode still makes a lot of sense for whenever you want to store anything. You want to store an audit trail, you want to store like the notes or the execution. Storing it inside GitHub makes a lot of sense. I think putting those two together is pretty incredible. So here we can see the final kind of agent notepad that was written. Sandboxes are all closed down and deleted now, so everything's been written out to directly to GitHub. And then in a second here in the video, we'll look at the actual outputs. So here you can see the runs. Let's go ahead and take a look at it here. You have the notes. Each agent was able to write exactly to one file inside of the GitHub repo, so no destructive actions would be possible. and then they were all summaries together inside one single example.
And one last thing to sort of note is one of the unique work that we did here on the network stack and the file system stack is that every time the policies are loaded, they're hot reloaded. So this isn't a traditional way where if you run in a container, you have to basically restart the entire sandbox and you basically have to wait for that latency. So this is another thing where we thought about this particular stack in machine speed for agent specifics. Every sort of millisecond of delay compounds downstream and ripples. So this is another thing that we really wanted to focus on. All right.
The next one we're going to show you guys, this is all of about 3 days old. But this is a really big piece of functionality we've been working on. Do you mind pausing it for 1 second there, Ali? So we have the OpenShell terminal on the left. We have a demo here on the right. And what we're demonstrating is this loop where an agent running inside of a sandbox is going to hit some sort of a limit, right? So in this case, we're directing the agent. We spun up, I believe, let's see, it's a Codex agent. We spun up inside of there, and we told it, hey, go ahead and write to GitHub. It starts with read access to GitHub, so it does not have write access to GitHub. So what's going to happen here is the agent is going to run. Let's go ahead and unlock it for a second. We'll let this run here. You can see the policies on the left. The agent's going to get blocked by OpenShell when it tries to write to the new repo. So here you say, it's going to be writing a policy block and drafting. So essentially, it's trying to write to GitHub directly. It gets blocked. We'll see the denial in a second. When the agent gets blocked, we pass it back an explanation for why it got blocked. We said, you got blocked because you don't have access to this repo. There's a local skill that you can use. And this is the kind of cool thing inside OpenShell, is that it's going to use that local skill, and it's going to say, hey, I can enumerate actually the sandbox policies, and I can also extend that policy. So it drafts a proposal and says, now I'm going to add, as you can see right here at the very top, this network rule that just got auto-approved here. It is requesting access to write to a specific repo endpoint. We've defined that that's okay. We can see this request here. So reason curl to write to one demo, so that's telling you what it's doing. Our prover is running against it, and it discovered one finding. So it discovered there that we were expanding the credential write scope of the agent, but that was okay. We automatically approve it, and we let it through, and it all gets logged. So here's the total logs that we have coming out of OpenShell. We use a format called OCSF, which is an open cybersecurity format. It's compatible with Splunk or any type of like security Datadog thing that you like to use. But you can see here, essentially, we have some approved accesses coming through here. We should see, let's look through here as well. Here, it first tried to do the write, so you can see it was denied. It's like, that's cool. It authored a new proposal as the next step. The gateway approved that, and then it was able to reload the policy, hot reload it, and then it was able to write to GitHub directly. So this is the kind of like neat like audit trail, automated approval process that we can do, that you can set security policy and then just let the agents evolve without having to grant this like massively scoped, like here's everything you can possibly do policy. We can keep each sandbox really limited to the minimal policy required, and the agent can negotiate its access from there.
And maybe just before we pause for questions, a couple of other just high-level notes on OpenShell. So we're building OpenShell with an ecosystem of partners. As mentioned, it's under Apache 2.0. Long-term thinking here is like this is something that we would potentially donate to CNCF or Linux Foundation. That's how we're thinking about it. Right now, the way we're actually implementing and taking to market OpenShell is we're working with partners like Microsoft announced this yesterday. It's embedded into Windows Native, WSL, Azure, GitHub.
MXC.
MXC. It's now available via Canonical on Ubuntu, Red Hat on OpenShift, Docker. We have partners who've discussed their work that they're doing, their agents like SAP, Workday, ServiceNow, running their agents inside OpenShell for trust. So the whole thinking here is like, how do we basically embed this as a trust layer and enable everyone to be able to build on top of it? So we would love for everyone, whoever has the time, to go to the GitHub repo, take a look, give us some feedback, experiment with it. This is really something we want community engagement with. While we are driving it at NVIDIA, our hope is that the community picks this up and pushes it out. And from a timing standpoint, we're targeting roughly the next couple of months for the beta version. This is still in alpha. We only released OpenShell at GTC in San Jose about 3 months ago in March. And now we are really maturing it around a few different areas. And some of the areas that we should talk about is that now we have this very cool and sort of powerful concept in OpenShell called drivers. It's exactly what you think. So when you are launching OpenShell, you can pick the perimeter for sandboxing you want under the hood. I want to use Firecracker. I want to use a hardened container. I want to be able to use trusted computing. I want to use SIG primitive sandboxing from Kubernetes. So we rely on whatever the technology is under hood for you to be able to use, and we enforce the runtime on top of it. All right, well, that's all we have for you today. We only have 4 minutes left, so happy to pause there, take any questions. Yeah?
So the agents can negotiate automatically to have their permissions elevated. How far can they negotiate that before it stops?
Our goal with this was to reduce, like, we finger in the air 90% of the approvals that a typical you would need. So the idea was that for any like piece of work you're doing, really ideally we could wrap it into 1 or 2 human approvals that were required for that. So that's what we that's what we aim for. But I think it really depends on what the security team, like the constraints the security team wants to build.
So in the project, like you have this concept of providers, like Codex, Claude, Copilot. These are all providers where central teams, IT, security, can run global policies. Now, every sandbox that we said starts with zero trust, so none of those are granted. So basically, the ceiling is whatever your central teams decide is the global policies your organization is allowed.
Yeah. But the idea is within that, the 2 ways that you could do this is like, one, you just give this massive, like, security signs off in this policy that is like the maximalist policy. It's like everything you could possibly do. That's not good from a security perspective. Like, not every agent should start out with that thing. So what we're trying to build here is a dynamic way for the agent to build into exactly what it needs, but no more. And so that's what we allow the negotiation really to happen right up until the point the security team says that's it. If it's anything more, then a human has to approve it.
And that's why we enforce it at kernel infrastructure layers, is we intentionally want that policy to be out of the path and reach of the agent, right? So it can't basically bypass it or override it or sort of reason around it.
Any other questions?
All right. Thank you very much, everyone.